Hi, in this video we want to talk about motion in a circle, and this video is keyed to Young and Freedman's University Physics Section 3.4, Motion in a Circle. Okay, well, we've talked a little bit about motion on a curve earlier in this chapter, Section 2 on acceleration vectors. I believe I have a video on that. When a car curves, the velocity, as it were, is changing direction. In fact, velocity is a vector. A vector is a quantity, a magnitude with a direction. Speed, speed, it doesn't matter what the direction is, but velocity is motion in a specific direction. And so when a car goes around a curve, it's constantly changing direction. And that means, by definition, its velocity is changing. And of course, what is a change in velocity? Acceleration. So by definition, if a car is going around a curve, it is accelerating in some way, positively or negatively. And so that the vector, the instantaneous velocity at any particular moment, is going to have two vector components. It's going to have the component of the velocity that wants to keep going in the same direction. You may have heard what we'll talk about in Chapter 4, a body in motion wants to stay in motion. Sometimes popularly we call that centrifugal force. Purists don't really like that in physics, but you may have heard of centrifugal force. That's the force that wants the car to keep going in the same direction at any instant that it's going, tangential to its curve. So the tangential component of the velocity is one component of the velocity. But if it's going around a curve, though, it also has an inwardly or centripetal direction to another velocity component. Or you might say, if it's going in a perfect circle, you might call that a radial component along a radius to the velocity. And of course, as I said, because it's changing direction, and here, listen to this, even if it's going at a constant speed, if it's changing direction, then by definition, it is accelerating, because it is changing velocity if it is changing direction. Okay, go back and see the last video if that didn't make any sense to you. Or that video in Section 3.2. Okay, remember from Section 3.2 that if, and we are talking about circular motion in this section. This section is about motion in a circle. Not a big curve or a real tight curve, but a circular curve, as it were, in this section. So if this thing going around in a perfect circle, if it's moving at a constant speed, its velocity is changing because it's changing direction. But if it's moving at a constant speed, then its acceleration is going to be exactly perpendicular or radial to its instantaneous velocity vector. It's going to be directly perpendicular to that acceleration, perfectly inward toward the center of a circle if it's moving at constant speed. If its speed is increasing, then its acceleration vector is going to be a little bit ahead of the perpendicular, because it's getting faster as it goes in the circle. And so its acceleration vector is going to be a little bit ahead of the perpendicular. If its speed is decreasing, then its acceleration vector is going to be a little bit behind the perpendicular. Go back to 3.2, watch that video on acceleration vectors if that doesn't make sense. Okay, well, and now it's time for bad drawings by Ken. So I've tried to represent this. Here we have a circular motion, and because the arrow is pointing that way, let's assume that it's moving around the circle this way. So if it's moving in uniform circular motion, what does that mean in this section? It means that it's moving at constant speed. So then the radial component, that's what rad means. It doesn't mean, man, this is a rad acceleration. Stupid joke. Anyway, it just means that the acceleration is going to be exactly perpendicular to the velocity vector, which is moving in a tangential direction. Now, Young and Freedman derive a couple formulas. If you want to know the derivations, go ahead and read those sections. It's fairly easy to understand. But basically, he derives this formula that says that the quantity, that is the magnitude of the radial acceleration, is going to equal the velocity squared divided by the radius. Radius, again, R stands for radius. And then, if you want to know it in terms of distance per second, he basically in radian measurement, and I have videos on radian measurement, the distance around a circle in radians is 2 pi r rather. And so another way to say velocity in regard to going around a circle is 2 pi r per time. So he substitutes that in for v, and he comes up with this other equation, that the radial acceleration is 4 pi squared r divided by t squared. If you want to know how to derive those, just read and reread those sections. However, what's important is that you can find these formulas when you need them, and here they are. Radial acceleration, if it's moving at constant speed, okay? Well, actually it works when it isn't. Next slide. But anyway, the radial acceleration is going to be v squared r divided by r, or 4 pi squared r divided by t squared. These two formulas are maybe even the main takeaway from this section of the chapter. Okay, well we can't leave without making your head hurt a little bit. So then he has another subsection to the section on non-uniform circular motion. What does that mean? Non-uniform means it's not moving at a constant speed. It's changing speed. So what if this circle was a roller coaster, to where you do the loop-de-loop, and so you might be going faster as you go down because of gravity, and then slower when you come up the other side because of gravity again. And so the radial formulas actually stay the same. But now we have another component to the acceleration. Because it's not moving at a constant speed, we have a tangential component to the acceleration. If it's moving at a constant speed, then there is a zero tangential acceleration. But if it is accelerating and decelerating as it goes around the circle, then it's going to have a tangential component to the acceleration. Here, when it's increasing, there's going to be a positive acceleration tangent component. Here on the other side, where it's decreasing, you're going to have a negative tangent component. But it's not hard. Basically, the velocity, the tangential velocity, okay, the instantaneous velocity that's going tangential to the circle, basically dv dt is the definition of acceleration. So the tangential acceleration is simply dv dt, where v here is the tangential velocity, the vector that's going at a tangent to the circle. Okay, now, what if you want to find the final acceleration vector? So see in here I've drawn final acceleration vectors. It's going to be the vector component, the vector addition of these two components, right? A here, the final vector, is going to be the vector addition of the radial component and the tangential component. How do you find that? Well, these are little right triangles, right? And so we're going to use the Pythagorean theorem. That in non-uniform circular motion, where we have both a radial and a tangential component to the acceleration, basically we're going to square the radial component, and we're going to square, I'm sorry, the t there should have been small. Always something. So the second one is a tangential, where the t should have been part of the sub part. It's not time. But anyway, so the radial component of the acceleration squared plus the tangential component of the acceleration squared. Take the square root of all that, and that gives you the vector acceleration, dv dt. That's the difference between the bracket, the absolute values being on the outside of everything, and the absolute values being on the inside. All that means is that this is just the derivative of the instantaneous velocity here, and then here, this is the derivative of the total velocity acceleration. Okay, just wanted to end this on a more complicated note than it had to be.